Unit 3, so we're on 3.1 in the notes packet. What we're going to be looking at this whole unit is systems of equations. There are 3 different methods for solving systems of equations that we're going to look at. The first one is graphing. So today we're going to focus on graphing. But before we jump into doing any examples, we need to talk about, y'all stop talking, face forward, stop talking, put your phones away. You need to be paying attention, please, and following along. All right, so we're going to fill in these blanks. We're going to fill in these blanks and talk about the different types of systems there are, okay, and how you can tell which type of system that you have in your problem. So first of all, what is a system? A system of equations is just when there's 2 or more of the equations. So a system of linear equations is 2 or more linear equations. Okay, so I'm just going to put that this is what we call a system of equations. Okay, and they can be graphed to find out if they intersect. Okay, so that's what we're going to focus on today, is graphing to find out if they intersect. Okay, if they intersect, the intersect is the solution. So if you're told to solve the system, you're looking for a solution to the problem. You're looking for the point where they intersect. Okay, so if 2 lines intersect, they intersect at a point, which means our solution is going to be written as an ordered pair. Okay, where it would be written like x comma y in parentheses like that. Okay, your solution is a point, and so it's going to be written as a coordinate point, as an ordered pair. Okay, now, if the lines do intersect at a point, they'll meet at a certain point, that means that they have exactly one solution. There is one point where they intersect. The definition of a line is that it goes on infinitely in opposite directions. So it never turns. So once those 2 lines intersect, they will never intersect again. They will only intersect at one point. If one of them turns to come back and intersect again, it's no longer a line. Okay, so there should only be one solution when we're dealing with those linear systems. Okay, now if that's the case, if the 2 lines intersect and they have exactly one solution, this is what we call a consistent and independent system. So when we talk about types of systems, this is one type. Consistent and independent. That's the first type of system. Okay. Another type of system is when you have the 2 lines graphed on top of each other. So if you graph one and the other and they're right on top of each other, that means that they are going to have infinitely many solutions. They are just the same line. So they don't intersect at one point, they're intersecting infinitely. Hold on, I'm misspelling it. So there are infinitely many solutions. This is also a consistent system, but it is dependent. Consistent and dependent. So this is our second type of system, is consistent and dependent. whereas the first type was consistent and independent. And that's when you only had one solution. I'm going to give you a visual of what the difference looks like here in just a second. Okay, the last type of system is when you have the two lines and they're parallel, which means they never intersect. We learned this back in Unit 2 that we just tested on last week. If lines are parallel, they will never intersect. They have the same slope. So that means that these have no solution. If the solution is where they intersect and they're parallel, they will never intersect, so there is no solution. Okay? This is called an inconsistent system. So your system is one of those three types: consistent and independent, consistent and dependent, or inconsistent. I'm going to have you flip over to the back of this before we even look at an example. Flip the page over to the back and look at this visual at the end of today's notes. Right here at the bottom are what those look like. Okay, we described them in words, but here's a visual. Consistent and independent means there's two lines and they intersect at one point, okay, and they have exactly one solution because they intersect at one point. So they are consistent and independent. If it is consistent and dependent, this is where we said it's just all the same line. It's right on top of the other one. Okay, so there's infinitely many solutions. Okay, and then the last one we said was inconsistent. Okay, that's when the lines run parallel. They never intersect. There is no solution. Okay, so those were those three possibilities. I'm going to keep that color coding the same as I did on the front. So I'm going to change this to blue. Okay. So let's try it. We're going to be given a system of equations. We're going to graph that. We're going to graph them and see, do they intersect at one point? Is it the exact same line, or are they parallel lines? Okay, and so we can state what the solution is and what type of system it is. Okay, so I'm going to flip back to the front now to start with number 1. Now, before we do this, last unit, in Unit 2, we said when we graph lines, we want them to be in this format. We learned that y equals mx plus b format was easiest to graph because you can see the y-intercept and the slope. So we like slope-intercept form. Okay, remember this is called slope-intercept form. So I want to get my equations into y equals mx plus b form before I graph them. It's going to be the easiest thing for me to do. All right, so I'm going to take, I'm going to do the bottom equation first. Okay, so this x plus 3y equals 18. I'm going to solve for y. So I've got to subtract the x to the other side because that's how I get rid of it on the left. And it leaves me with 3y equals, I cannot combine the 18 and the minus x. One is a variable term, one is a constant. They do not go together. I want them in this format though. I want the x term first and then the constant. So I'm going to write it as negative x plus 18 instead of 18 minus x. Now the y is still not alone. It's still not isolated. There's a 3 in front of it. So we're going to divide out the 3. Remember, the opposite of times 3 is divided by 3. That's how we're going to reduce it over here to just y equals. But what we do to one side, we do to the other. So we have to divide everything over here by 3. So the x term gets divided by 3. And right now, what's the coefficient in front of this x if nothing's written? There's no number written in front. What is it? A 1. Now there's a negative, so it's a negative 1 divided by 3. So it's going to be negative, bless you, negative 1/3. And then you still have the x. And then what's the 18 divided by 3? 18 divided by 3. Thank you. And it's positive. That was a plus 18 divided by 3, so plus 6. Okay, so that's the first equation. I'm going to go ahead and I'm going to come over to my graph and I'm going to graph it. Okay, because the y-intercept is b, so that is the plus 6. So I'm going to go to 6 on my y-axis and plot that point. And then I'm going to count my slope. My slope is negative 1/3. Remember, your slope is rise over run. So the fact that it's negative means I have to go in a negative movement. Okay, I can either go down 1, right 3, from that y-intercept that I just plotted, down 1, right 3, down 1, right 3, or I could go up 1, left 3. So I get myself several points for the first graph, and I draw the line through those points. Okay, so there's that line for this one. Now I need to do the same thing for that first equation, okay? But I'm going to have to rewrite it either off to the side or down below here. I guess I'll do it off to the side over here. All right, so I need to solve for x, or excuse me, solve for y. So I'm going to move the x by subtracting minus 2x, which leaves me with negative, oh, that is a plus. So it leaves me with y, it's going to be positive. And then I cannot combine those, so I'm going to write the x term first and then the constant. Now this one, there's no coefficient in front of the y, so there's nothing to divide over, so that's it. That's my equation, and y equals, so now I'm ready to graph that one. So it's got a y-intercept at 11, which I'm going to move this where I pointed and said that was slope. Move it above. Because that 11 is just off up here. If we count up from the origin, 11 would be just above the graph here. That last line was 10, so here's where 11 would be. Okay, and then we have a slope of negative 2. So that means we're going to go down to right 1. Down to right 1. Down to right 1. Down to right 1. You can get as many as you need, but hopefully you noticed we just drew a point on top of one of those gray points. So when we talk about where do these intersect, we just plotted a point where they intersected right here. Okay, so that is where they intersected. Okay, this is the point of our solution. Remember, your solution is written as an x, y, as an ordered pair. So my solution here is at, let's see, that's over 3, up 1, 2, 3, 4, 5. So my solution is 3, 5. That's the point where they intersect. Now it also asks me, it says determine the solution up here, find the solution and the type of symmetry, the type of system. Okay, so there were 3 types of systems. We said here they're either consistent and independent, consistent and dependent, or inconsistent. Which type was this that we just did? This blue, green, or pink one? Blue and green are both consistent. This is consistent and independent. This is consistent and dependent. So which one looks like what we just did? The blue one right here. There's an intersection of 2 lines. That's what we just got. We got an intersection of 2 lines. Okay, so this is the consistent and independent. Okay, so this is consistent and independent. That's the type of system. Do you feel okay about that? Okay, let's try this next one then. We're going to do the same thing. We're going to get both equations in y equals, and then we'll graph them and see, do they have one solution, infinitely many solutions, or no solution? So I'm going to take the bottom equation and I'm going to go ahead and solve this for y. So I'm going to subtract the 4x over. So I've got 2y equals negative 4x plus 12. Now I need to get rid of the coefficient on the y. That 2 needs to be divided. But again, everything gets divided by 2. So that leaves us with y equals, and then this would be negative 4 divided by 2 would be negative 2. Still have your x. And then 12 divided by 2 would be 6, plus 6. So that's the first equation I'm going to draw, or graph. Okay, so I'm going to come over here to my new graph, and I'm going to go up to 6. About my point, that's my y-intercept, and I'm going to count my slope of negative 2. So that's down to right 1. Down to right 1. Or you could go up to left 1. Okay, but you get enough points. Well, hopefully you draw a better line than me and it actually goes through your points. I'm going to try that once more. It's better. So you graph your line. Now we're going to do the same thing again with the second equation, or in this case, the first. I did the second one first. Okay, so I have got 2x plus y equals 3, and I need to solve for y. So I'm going to move the 2x by subtraction, which leaves me with y equals negative 2x plus 3. So I cannot combine those because one is a variable and one is not. So now it's in that form, mx plus b. So my b, my y-intercept, is down at, or up at 3. But what do you notice about the slope of this one? Look at the slope of both of these equations. What was the slope of the gray one? What's the slope of the yellow one? Also negative 2. And so if I continue to graph this down 2 over 1, and I draw this line, Are these lines ever going to intersect? No, these are parallel lines. Parallel lines do not intersect, okay, because they have the same slope, but different. Spelling different, man. Happy Monday, y'all. Different y-intercepts. Okay, the y-intercept was different. The slope was the same. So same slope, different y-intercept. These are parallel lines, which means there are infinitely many, or I'm sorry, go back up here and you can see it. Parallel lines never intersect. There is no solution. This is an inconsistent system. And you can see the graphic on the back. When the lines are parallel like that, it's an inconsistent system and there is no solution. So I meant to be writing that in red. So I'm going to rewrite this in red so my color coding is accurate. Okay. The same slope, but a different y-intercept. Means you have parallel lines which is no solution because they never intersect, so there is no intersection point. And so the type of system is inconsistent. So we had a consistent and independent last, and now an inconsistent here. So far, so good? Now let's see what happens on number 3 here. Okay, I'm going to go through solving of the second one first by subtracting the 2x. Remember, I keep those separate because one has a variable, one doesn't. Okay, now I've got to get rid of the -6 in front of the y, so I'm going to divide it over. Now that does isolate my y, which is the goal, but looking here, I get a negative divided by negative, which is a positive, and 2/6 is 1/3. So positive 1/3 x, and then 10 divided by -6, that's a positive 10 divided by -6, so we're going to get negative, and that's going to reduce to 5/3. So I'm not actually going to graph this yet because that's a more complex one to graph since our y-intercept is at a fractional value, not an integer. Okay, so we'll come back to it in a second, but we got this equation in y equals. Now we want to do the same thing with the first equation. So we've got x minus 3y equals 5. Okay, we're going to subtract the x to the other side. Needs to be with -3y equals -x plus 5. And then I have to divide the -3 across. And here's what happens. The negative divided by negative is a positive, and this is an understood 1 in front of the x, so this is positive 1/3. X, and then 5 divided by -3 would be -5/3. What do you notice about these two equations? Not only are they the same slope, they're also the same y-intercept. Okay, so they are exactly the same. This is when out of here. This is when there is infinitely many solutions because they don't just intersect at one place, they're constantly intersecting. They're the same line. So there's infinitely many solutions. And the type of system it is, when they're the same line, infinitely many solutions, that's consistent and dependent. Consistent and dependent. I'm not even going to bother graphing in this case because I can see the equations identical and they're going to intersect everywhere. I don't even have to have a visual of it if I can see it in the exact same equation. So far, so good? All right, now let's look at this very last one. We've had one of each style so far. We've had one with one solution, we'd have one with parallel, and now we've had one that's the same line. Okay, so let's take a look at that last one and see which one it's going to be. I'm going to do the same process. I'm going to solve this equation for y, or sorry, for, thank you. We're going to solve for y by moving the x. Okay, and then divide out the 6 to get the y by itself. So the 3/6 reduces to 1/3 x, and the 12/6 is just a 2. Okay, if you don't want to graph it till the end, okay, because you want to make sure they're not the same before wasting time graphing, that's fine. We can wait and see what the equation is. Oops. We can wait and see what the equation is before we decide if we need to graph it to see the solution. Okay, so I'm going to solve 2x plus 3y equals 6 now by subtracting the 6 over. I've got negative 2x plus 6, and then I need to divide the 3 over. Now when I do that, I get negative 2/3 x and then plus 2. That is a different equation. And looking at the slopes are not the same, are they? So I can tell by looking at this which type it's going to be. The slopes are not the same, so it's not parallel, it's not the same line. It's going to be consistent and independent. But I don't know what that one solution point is going to be until I graph it. So in this one, I do need to graph. So the yellow one, it said 2 and then negative 2/3. So down to right 3. So you get yourself a handful of points and get that line graphed. Okay, and then the other line also had a y-intercept at 2, but a slope of 1/3. So that's rise 1, run 3. So you get yourself a handful of points and you draw that line. Now we can see where those intersected. They had the same y-intercept. So that is our solution. What is that point? Where did they intersect? How would I write that as an xy? What is that point where that intersection is happening? From the origin. So if I start at the origin, how far did I go left or right? How much did I go up? Went up 2 from the origin. Did I go left or right any? No. So that's 0, 2, because I went left or right 0, but I went up 2. So the solution is at 0, 2. And we already said that that makes this a consistent and independent system. Okay, so again, your job is to determine if it is consistent and independent, consistent and dependent, or inconsistent. Is there one solution, infinitely many solutions, or no solution? Which of these 3 cases is it? If it is the one solution, you do have to find what that one solution is. Okay? So really, the ones that are consistent and independent, those are the only ones you have to graph. If you can see from the equation that they're exactly the same, then you know there's infinitely many solutions. If you can see from the equation that they have the same slope but different y-intercepts, then you know they're parallel, which means there's no solution. Okay, so we didn't have to graph the parallel lines to know that. If you understand that parallel means same slope, different y-intercept. Okay, so I'm going to pass out the practice. The practice is only 6 questions, so we're actually going to assign it all. I know a lot of times we shorten up the assignment because they're long. This is not a long assignment. It's only 6 questions. Okay, and it will be due by Thursday. Remember, this week is a short week. We don't have school Friday, and Thursday is the end of the grading period. Okay, so this is due by Thursday of this week. Good? All right, then I'm going to pass it out and let y'all get started. You can use the notes. You can work with a partner or a small group if you'd like.